Okay, geographers, back at it, doing more GIS work. And what we're going to do with this video and this exercise is we're going to get a brief introduction to digital elevation models, what we call DEMs, and also this concept in GIS called surfaces. And it has to do with taking a DEM and modeling, creating some element of the Earth's surface. And you'll see what I'm getting at when we start to get at it. All right. And so we've got here on the screen this black and white and gray square. That's our digital elevation model, our DEM. And I access this through the USGS. A whole lot of acronyms coming at you now. In Canvas, I have this zipped and uploaded. You should be able to access it there, download. It's a big file. So it might take a while. Be prepared, download it. Pause this and start downloading and let it all come down and be ready to go. If you have any issues with it, let me pull this over. I got it from the United States Geological Survey, and it's the National Map TNM download. And what I did, if I go back here, if you just do USGS TNM download, there are a bunch of different things that pop up. But what we're looking for is this screen right here when you want to access this stuff. And you can, copy this stuff here. It always changes. They do little updates or what. It can be confusing. So just know you're looking for USGS National Map download. And it's in this elevation products category. And what you do, well, first you go to a location. You can type something in and search. You can zoom in to an area. I was interested in this area, the Pacific Palisades and the surrounding area, because of recent fires there. As I'm recording this, the still dealing with these fires. I'm actually staring at my phone right now because there's a fire that seems to be okay in terms of where I am and where it's at, but still monitoring because this is Southern California. This is the West in general. We're dealing with this. We're in it. And so we're going to look at how to do some, kind of general GIS things, but we'll connect it to wildfires and some of the ways in which we study where these fires are burning, where they're going to keep burning, and all of that. So if you select here, just got a text from a friend, just constant people in other parts of the country checking like, you okay? You on fire? So all right, let's get through this before I got to evacuate. So check on this elevation products, and what we're going to look at is this 1/3 arc second DEM. When you're zoomed into the area, you have this selected and hit search products. It will give you what's there, what exists. And if you bring your cursor over here, it highlights the or shades in the area that's covered, right? So this first one covers the Palisades here, this whole region. And you would just hit download link and it downloads that TIFF file. Okay, that's how I got the thing that I put into Canvas for you. So if Canvas is giving you trouble, you can get it directly from right here. And it's a way to, if you want to explore other places, get data from other parts of the country. This is a great resource. All freely available. Your tax dollars already paid for this stuff. So you can download it, unzip the stuff, bring it into ArcGIS Pro, and have at it. Okay? But I have it here from Canvas or from the USGS, wherever you want to get it from, I've got that. I also have in Canvas a separate little shape file. I did this separately just to make this an easier thing to download and not make it too complicated with dealing with big files. But I made this Pacific Palisades outline just based on the zip code for the region. So this pink down here is another thing you can download to show you if you're not familiar with the area. In fact, let me turn that off. It's down here outside of Santa Monica along the coast. So this is one of many areas that, recently have been dealing with fires, and over, last couple of decades, all of California has been dealing with a lot of these fires. So let's look at this here. And what we're going to do is use this DEM to get a sense of what's going on, what the Earth looks like here in terms of elevation and some other elements of just the Earth itself. Okay? Okay, so DEM. This is what it looks like, just kind of raw, ready to go. We're not going to leave it like this at all. We're going to be doing some stuff here. First thing we want to do is we want to project this DEM. Just will make life easier. And the reason why we want to project this is A, it's always good to get all of your data in the same projection, same coordinate system, all of that stuff. But with this, these are in these arc seconds, which has to do with, the degrees, minutes, seconds, and the curvature of the Earth and all of that. That's how the data are stored through the USGS. The elevation values are in meters, okay? So XY values, okay, where these little grid cells are located, that's in this weird arc second thing. But the actual number, the value of any of these cells, that's the elevation in meters, okay? So we want to get our X, Y, and Z. So Z would be the elevation coordinate. We want to have them all in the same unit. We're going to keep it all in meters here. And that's just, it makes life easier when you start to do some of the analysis, you start to run some of these tools. If you don't have everything in the same unit, you got to do a little math here and there. You got to remember this stuff. It can be a pain. So first move, going through geoprocessing. You can, either, again, analysis, click tools, or just pull it up in your tab. In find tools, let's do project. And remember, we need to do project raster because it's a different tool here. We're working with a raster data set. So we'll click that. Input raster, it's the only one we got. Output, I'm just going to call this my DEM. I don't need to know exactly which one it is. And this gets into, latitude and longitude values. You can learn how to read the file name that the USGS gives all of this stuff, but we don't really care. We're not comparing multiple ones. So I'm just going to call it DEM. Okay. Output coordinate system. I need to select one. And what we're going to do here, like UTM, but this time we're going to use state plane because that's one that we encounter quite a bit as we're working with local government data and all that. So we're going to open up state plane. We're going to select this third one. So North American datum, 1983, parentheses, 2011, meters. I want to work with meters. I'm going to open that up. I'm going to skip these garbage states. No offense, other states, but come on. Look at that. I still have that California native pride, even though this state is engulfed in flames right now. So we're going to come down to California. We have these different zones, so the Roman numerals here. And for NAT 83, we're going to select 5, or V, for Los Angeles in this general area. Yeah, it gets a little confusing. I think it's zone 7 if you're using the 1927 NAD. It's all a mess. But what you can do if you don't know which zone you're in with state plane in a place like California, quick Google search. Tons of maps that pop up. You can find some good reference that will show you graphically like where you are in the state, what zone it is, and all that. But we want this one here. So NAD 1983. Okay. All right. Sorry about that. My video thing just crashed, so I'll just stitch what I got to this new version here. We should be good. All right, moving forward. So, added that. What you didn't see is I just hit like OK or whatever to select that California state plane zone 5 thing right there. So that puts this in here. It adds this little transformation thing that just did it. I'm cool with that. For resampling technique, this is important. We want to select bilinear interpolation. And the idea is we're dealing with continuous data, this elevation stuff, meaning there's elevation values everywhere throughout the resampling place. We're going to make this new DEM. Nearest neighbor, not the best choice for continuous data. Bilinear, much better. So that's why we're selecting that. This output cell size, all this, I'm going to leave it alone. Let it do its thing, because that's not really relevant to what we're doing. Double check it. Looks good. I'm going to hit run. And hope with the way everything is going these days that it all just works. And it might take a little while. We'll see. I might be stalling, vamping a little bit, depending on how well this works. Because it's a big data set. You saw this as you started downloading it. The fact that there's no progress right now frightens me a little bit, but we'll see. We'll overcome. But in the meantime, while we're waiting for this, let's talk about what we're trying to accomplish. Oh, look, it just happened. Okay, and look, it's there. Okay, no, this is good. Forget it. We're not going to talk about what's going on. We're going to get into it. I thought that would take longer. So we have, it's hard to see, but we have two, one on top of each other, DEM and this USGS, blah, 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 blah. So I can get rid of this one. I go ahead and remove it just so I don't get confused. And it looks effectively the same, right? Some little tweaks in the lines right here and all that. But what we did was we just projected this into this state plane system, and it should all be good. Okay, now what we're going to do is let's turn this DEM into something that, makes a little more visual sense to us, right? And this is when we get into our surface work. So I'm going to come back out here to this main area, and I want you to go to toolboxes so you can see where this stuff is. And I'm going to scroll down here to good old Spatial Analyst tools. And I'm going to keep scrolling down here, and I'm going to go into Surface. Okay, and we've got a lot of stuff in here. And what we're going to do first is what's called hillshade. It's hillshade in ArcGIS Pro and all the Esri stuff. Shaded relief is another term. But we're going to make this look like the actual mountains and valleys, like the actual earth itself. And the way in which this works is it models if the sun were shining from a specific, altitude in the sky. So it defaults to 45 degrees up in the sky. And azimuth has to do with direction. Okay? And its direction works with north up here where my cursor is 0 degrees. It's also 360 degrees. So we'll start with 0 up here. And as you move around directions, you can think of this as a big circle, right? So we move over here to the east. Due east would be 90 degrees. South is 180. West is 270. So this azimuth of 315 means that the sun would be somewhere over here in between, north and west. It would be in the northwest, okay? And at the same time, it's over there, and it's at this 45-degree angle. This is what it defaults to. It might not make sense depending on where you are, the region, what the sun's actually doing, but it just seems to look the best this way, which is why they've always had this default setting. So we're going to leave that. For input raster, we're going to select DEM. Output raster, it does this default hillshade underscore DEM. Let's just call it, we don't need to be silly. I'm just going to call it hillshade because that's what it is. This model shadows, I've never been thrilled with it. I'm not going to check that. And this Z factor, this is a key thing to be aware of. We don't have to do anything right now. And that's because we went through and projected our raster. So what it's saying for the Z factor is it's basically saying, hey, do you, with your X and Y units, is that different from your Z units? We just projected it, so no, there's no difference. So we'll leave it as 1. But if there were some difference, like if we didn't project this, that we would type in here, it would actually, for this type of DEM, it would be 0.00001 is what you multiply your Z values by to make everything look right. Gets a little confusing. Easier to project it if you can get away with that. So we're going to leave this as is, but this is always something to be aware of, right? Also, if I had, one way to think about it is if I'm dealing with, feet for X and Y and meters for Z or vice versa, this is where I could put in that conversion factor to kind of, treat the Z factor as the same as the XY. But again, if you can just project it, way better. So I'm good here. I'm going to hit run. And a lot of this stuff is things you kind of learn as you go. Can be a pain to kind of figure out. But, luckily the internet is there. And you see pretty quickly, hopefully we won't see it here, but you'll see when you run this and it just looks wrong, something's up, right? And it's either your original DEM that you have, it's maybe it's your Z factor in there, like there are different things that work. But this is more or less what we want to see. And it's not the prettiest zoomed out, but as we start to zoom in, it's kind of pixelated. Let's let it catch up and draw itself. Here we go. That's looking better. But what you can see are actual mountains, ridges and valleys and things like that. These are kind of weird. In fact, let me zoom back out. Let's go actually closer to the Palisades down here. And let's come to this area. So what we've got with this is you'll see these little artifacts. Like these are clearly roads that we're dealing with, right? But they look kind of weird. The DEM has been scraped. That's a term that's used. A few different terms that are used for this stuff. But the effort has been undertaken to remove the built landscape to simply show the natural landscape. It doesn't always work. It's not perfect. It's done with an actual algorithm, right? It's not people going in and changing values or erasing stuff. So you get these little artifacts that exist. But the idea is that if we remove all the buildings and roads and stuff like that, it's easier to, just look at what the natural landscape should look like. It's also useful for modeling like flooding and water flow and different things like that. Or what we'll be dealing with is slope aspect, some of these things. It's nice to not have all the buildings in there to kind of muddy it up. So you'll see weird little geometric patterns and things in here. That's what we're dealing with. And for what we're doing, this is actually good. Okay, you can see more roads up here. But the main idea is that we see the hills, We see the mountains, see valleys, see these different canyons and stuff like that. That's what we wanted to accomplish. And I'm going to go ahead and hit save right here. Now, from an analysis standpoint, hillshade, not very useful for calculating different things, modeling different things, but it looks pretty good, right? And keep in mind too, this is a free data set that we downloaded, this free DEM. It's not going to be as high resolution, as slick as some other stuff that's out there. If you work with a government agency, there's a good chance they've paid for really high resolution digital elevation model data for the area in question. Back when I worked in industry, I worked for some places where they had that, and it was so cool. This massive data set, and you could pull it up and you could make gorgeous maps, and it was all clean and looked really nice. You could zoom in. It was great. All right. When you're a college student just learning this stuff, you don't have that luxury. So we're learning how to do this stuff, but keep that in mind. Depending on where you work, you can get some cool stuff. But even, that said, this is pretty cool, especially if you're zoomed out, enough, you can kind of get that pattern of what's happening. Can look pretty nice. But once you really start to zoom in, you can see here, it's pixelated, right? And gets kind of hideous. So just keep that in mind. There are some limitations to what we got here. But if you can, also always use this stuff. Put this into your maps. I had this one boss I worked for. He was, bless his heart, he was easy to, I don't want to say manipulate, but easy to persuade, right? Or impress, or whatever. If I put in a hillshade to any map whatsoever, he was blown away. It was so cool. Now, granted, this was like 20 years ago. This is before this was, we had Google Maps and Google Earth and a lot of this stuff where we can take this for granted. But I would do this, and it was effortless to put it in, but he thought I was a genius. And then conversely, I did some analysis that was like really hard, and I was really proud of what I did and the results I got, but I didn't put a hillshade in. He wasn't impressed at all, right? So I learned just everything. Make it a sexy map. Put in that hillshade. So that's how that's useful. But at least it gives us a sense of what the area looks like. Okay. So we got that. Now let's actually get into some other surfaces that are a little more useful. All right. The first one we're going to do is called aspect. It's in the same surface area. But aspect refers to the direction a slope faces. Okay. And this is something that's important for a variety of things. In fire, studying an area, seeing what fires are going to do or what's fire prone or all of that stuff, aspect plays a role. From what I've looked up, and I'm not a fire guy, so I could be mistaken with this. Maybe Southern California is different from what I've found, but like in reading some articles and all that, it was saying northern facing slopes and eastern facing slopes are more dangerous than southern or western facing slopes. And it has to do with, the amount of sunlight and heat and what that means for vegetation and fuel. And here too, it can also be affected, with winds and stuff like that. Wind direction. I don't know. Again, not a fire guy, but this is a very valuable thing to study for people who study this stuff, right? And get a sense of if we have a fire going, where is it spreading to? What's what are areas that are more dangerous, right? Or areas that are a little safer. Maybe we're in an area where it's not currently on fire. But one thing we as Californians really need to do is assess where stuff is, currently built. Look in these neighborhoods and communities and get a sense of is this place doomed if, the slightest spark goes off? And where can we kind of clean up some vegetation, use some more fire-resistant building materials and all of that? This is good kind of preventative analysis, which is what we need to do. So, okay, aspect. All right, input raster, DEM. We're not going to do anything off of our hillshade. We always want to be working with the original DEM. Output raster. I don't need this whole deal. I'm just going to call it aspect. Okay, method. You have planar and geodesic. If you're dealing with projected data and it's over a relatively small area, this is totally fine. This is a 2D model. The geodesic takes the curvature of the Earth into account. It takes longer to run the tool and all that. For what we're doing, this is fine, right? The curvature of the Earth doesn't really, affect us here, especially if we're looking at a specific area, down around the Palisades, say. So I'm going to hit run. Just let that move. And as I've said before, always, if you have any doubts with what some of these different options are, click on the little, help button thing, more information button, do some Googling, see what comes up. All right, this worked. Believe it or not, this is what we want right here. So it's horrendous. This is like an acid trip, right? Staring at this thing. But this is what it's doing is it's using color to indicate the aspect of a slope. Okay, so gray, and you can see in the contents pane, gray just means it's flat. Okay, there's no aspect because there's no slope. And we have that for the ocean out here. Okay, red means it's a north-facing slope. In this case, it's 0 to 22.5 degrees. Okay, which would be 0 would be perfectly up at the top, and then going 22.5 degrees over that way to the east. Okay, if you note at the bottom, there's also red. If it's 337.5 to 360, that's just, 360 is the same as 0, and it's just over on this side. So anywhere we see the color red, it's indicating that slope is facing north, right? And then northeast, east, southeast, south, and so on. It gives us those colors. Now, simply producing a map like this, not the most useful thing. It's you can see it visually, it's much. But what we can do, we've already done reclassification stuff, and I'm not going to make you do this, but you could do this if you needed to, like with the hurricane stuff we did earlier, or any of these other analyses. We could just say, okay, we know north and east, those are bad. We could lump northeast into here as well. And so we could reclassify it as, anything that's 0 to 112.5 degrees in terms of azimuth gets like a 1, right? For that's bad. Everything else could just be 0 in terms of not as scary, right? If that, were what we wanted to do. We could also have different variations. We could reclassify it having, 1 through 5, making 5 the worst and 1 the least scary aspect, however you want to do it, right? But it's really useful to be able to transform this into something that's a little more simplistic, right? And just says good, bad, right? Or, bad, worst, apocalypse, or however you want to do this stuff. Okay, but that's how that works. The other surface we're going to do, and I just want to introduce these things. We're not going to really derive any answers from this. I just want to have you play around with these surfaces. So we'll leave this right here. In fact, what I'm going to do is I'm going to uncheck that because it hurts to look at. But the next thing we're going to do is slope. And we can do one of two things. We have, if we go back, you can find the slope tool in that same area. There's also this surface parameters tool that is relatively new in ArcGIS. And it said, if I go, actually, let me do, I'll go back to aspect. So it says provides enhanced functionality or performance. And if you notice when I went back there, this is in that same surface toolbox. But if you click this one, it gives you options. So parameter type, if I hit the drop down, slope, which is what we're going to do, but see aspect is there. So we could use this as well to get the aspect and other things that are in here, right? Some stuff you might want to use, some stuff doesn't matter, whatever, but they say this gives you more functionality, a few extra little, input things, parameters, stuff like that in here. So we'll use this one for slope. So input surface raster, going to use DEM. Output raster, we're going to not call it surface DEM, that's confusing. We're going to call it slope. And I'll put slope, and I'm going to do an underscore and percent, because we're going to do it in percent. I'll get that and do it in a minute. Input analysis mask. Okay, let's try this. Let's do Pacific Palisades. And with this, the mask idea is, again, just do the analysis in a certain area. Okay, parameter type, slope. That's what we want to do. Local surface type, you have two options. Quadratic is better, right? 4 versus 2. It has to do with, I think it's the smoothing is what that one is. So we'll leave that there. This stuff we'll leave. Z unit is in meters. And then slope measurement, we're not going to do degree, we're going to do percent rise. And the reason why we're going to do this is because the thing that I was looking at, the article about fire issues, it used percent rise for the slope. I'm looking over my other screen to see where that was. Yeah, it was 15% or greater slopes are at greater risk of fires spreading and continuing to spread and all of that. You can look up the difference between degree and percent rise and how we measure slope, but this is something to just be aware of. If what you're looking for has to do already with a percent slope, go with percent. If it's just a general slope map, degree is kind of better because it's a little easier to conceive of. We can think of, 0 and going at 45 and 90, that all kind of easily makes sense. I had one project I was working on where we had to do the slope in percent. I forget why exactly, but that's just what we did. And the guy was working for a different boss, not as lovable as the other one. He could not grasp percent and slope and how this works. And he was accusing me of doing like sloppy work, when the reality is he didn't understand some kind of basic mathematic principles, even though he claimed he was this brilliant math and science guy. But just be aware, right? If it's kind of a more generalized audience, go for the degree, whenever you can. With this, we're going to go ahead and do percent rise, and we're going to see what's going to happen. So that looks good. What do you mean it doesn't have a vertical unit? It does too. Well, I think it'll be okay. Told it meter right there. Let's see if this is an issue. Beautiful. Look at that. It's contained within this this little Palisades area, right? And what it's showing is these darker blues that we have is effectively, flat or a gentle slope. And then it goes into these lighter blues and greens and yellows. You can see the legend over here. The yellow is, really steep. But with this, you can see in this region, pretty much, we said 15% or higher are at risk. That's most of this area, right? In these different canyons and all that. And yeah, houses are built in these little, flattened plots and all that. But this whole area, one of the issues we've had is, not just shocking winds that have come through and dry vegetation and all that. But the terrain itself is a problem when it comes to fires. All right, so that's how we see that. If I also wanted to, just to show you and to get a sense of stuff, I can switch that to degree and we'll do degree. I'll run that as well. The end result looks the same in terms of this color scheme that it imposes on these slope surfaces. So there you go. Same kind of deal, right? And it looks pretty much the same. Don't see much difference, but the value is in degree, right? And that's because the slopes are the same. It's just a different way of representing slope, okay? But if I have this, see, like here, this idea of a 293% slope, if you're thinking in terms of degree just kind of by default, that seems weird. What does that even mean? It's like flipping around a few times, or like what's going on, right? Whereas this is 0 to 90, with 90 being a complete cliff, so I can look at this and get a sense of, oh yeah, I can relate to that stuff. You follow? Hopefully you follow. All right, I'm gonna hit save. Here's what I want you to do. We're gonna end this here. What I'm gonna have you turn in is another one of these things where it's either one layout or 3 separate layouts, but I want you to show me just for the Palisades area. So we're going to use that input analysis mask, which I don't think you could do when we just did aspect, right? Didn't have that option. Now, you could get into environments and do that, but what you might want to do is do a surface parameter thing. But go ahead and make me 3 maps. Again, either one layout, 3 different layouts, showing the hillshade, okay, just so I can get a sense of the terrain here, the slope in percent, and aspect just for this Palisades area. Okay, make sure to put in a legend so I can see what it is I'm looking at, because this stuff can be a little misleading, but that's all we're going to do. We're not going to get in and reclassify. And again, what you could do, you could select aspect that's scary. You could select slopes that are scary. You could add these things together with some of that raster math stuff like we did back with that hurricane stuff, and really start to add on to it. We could get some vegetation data as well. Add that here. We could see the places that are just the most susceptible to going up in flames, and then places that are less at risk. And that way we could target our forces. We could figure out, some preventative measures in areas before it gets to this point, right? Or again, send our firefighters in there and see which are the places where this fire is definitely going to be growing and spreading to, and all of that, right? So a quick introduction, not going to do everything we could do, but I wanted you to see how these different surfaces work. So give me my maps. Happy working, happy mapping. I'll see you in the next video.